Hello everyone, welcome to my class. In today's class we'll start chapter 10 and today I'll cover sections 10.1 Sequence of numbers and series. So let me begin the class right away. First I'll talk about sequence and its notations, and in second I'll talk about series and its notations. So first, definition of sequence. A sequence is an ordered list of numbers, such as here the list of even numbers 2, 4, 6, 8, 2n, Second, this is a list of odd numbers. Third, this is a list of reciprocals of natural numbers. Each number in the sequence is called a term. We define the terms in the sequence using their positions, and later we use a formula to find the nth term of the sequence. Quick example, here is a sequence whose terms are a1, a2, a3, an, So here a1 is the first term of the sequence, a2 is the second term of the sequence. Similarly, an is the nth term of the sequence. Notation of sequence. We denote the sequence by little an and enclosed in the curly brackets, and here the suffix n from 1 to infinite. If this is an infinite sequence, if it's a finite sequence, then n goes from 1 to the finite number, or simply by little an enclosed by this curly bracket. Quick example. First example, sequence n, that's the sequence of natural numbers whose terms are 1, 2, 3, Second example, sequence of 1 over n whose terms are 1, 1/2, 1/3, Example third, sequence of 1 over 2 to the power n whose terms are 1/2, 1/4, 1/8, and so on. There are two types of sequence, finite sequence and infinite sequence. A finite sequence has a finitely many terms, whereas in infinite sequence terms go on forever. Example 1. Write the first three terms of the sequence defined by the explicit formula given in A and B. In A, the formula is an equals to -1 to the power n times 2n plus 1. So begin the solutions. So put n equals to 1, n equals to 2, n equals to 3. That gives us a1, a2, a3. These are the first three terms of the sequence defined by this formula given in part A. So here, put n equals to 1, put n equals to 1, then a1 equals -1 power 1 times 2 times n equals to 1 plus 1. Simplify, this gives us -3. Similarly, for second term, put n equals to 2, then it gives us a2 equals to 5. Similarly, put n equals to 3 in the formula, then we will get a3 equals to -7. Hence, the first three terms of the sequence given by this formula in A is -3, 5, -7. I hope this makes sense to you all. Now let's answer the part B. Here the formula is an equals to 1 over 2 to the power n. Begin the solutions. To find the first terms, second terms, third terms, put n equals to 1, n equals to 2, and n equals to 3 respectively. So here, put n equals to 1, then we'll get a1 equals to 1 over 2 to the power 1, which is simply 1/2. Similarly, for second term, put n equals to 2, then we'll get a2 equals to 1 over 2 raised to the power 2, which is simply 1/4. Similarly, a3 turns out to be 1 over 8, and so on. Alternately, a sequence is a real valued functions going from set of positive integers to the real number, and we denote it by an equals to f of n, and sometimes a of n is written as a suffix n. So in a sequence, the inputs are natural numbers. We can plot the terms of the sequence using bullets and join them by functions having finitely many discontinuities. So for example, when input is 1, output is a1, so the order pair is 1 comma a1, so we graph here. So we plot this order pair here. Similarly, when input is n equals to 2, then output is a2, so we have an order pair 2 comma a2, and we plot that order pair here. Similarly, for any input n, the output is an, so we have order pair n comma an, and we plot the order pair here. Then we join those points. Awesome. Now let's move on. Alternating sequence definitions. Alternating sequence. An alternating sequence is a sequence where the terms alternate in sign. For example, sequence an equals to -1 to the power n times n. So here we put n equals to 1. That gives us here -1 power 1 times 1 is -1. Second term, put n equals to 2. -1 square is +1 times 2. So we have +2 and so on. Next definition, increasing sequence and decreasing sequence. An increasing sequence is a sequence where each term is larger than the preceding term in the sequence. Similarly, a decreasing sequence is a sequence where each term is smaller than the preceding term in the sequence. For example, sequence of 2 to the n is an increasing sequence. So here, each terms are bigger than the previous terms. Similarly, the sequence of 1 over n square is decreasing sequence. So here each terms are smaller than the preceding terms in the sequence of 1 over n square. Next definitions, recursive sequence. Or sequence is called recursive if the formula defining the sequence uses the preceding terms. A recursive sequence must give initial terms called seed term. Example 2. Write the first 4 terms of the sequence defined by the formula a1 equals to 2 and an equals to 5 times an minus 1 minus 3 for n greater than or equals to 2. So let's find the first 4 terms. So a1 is given to us. Let's find a2, a3 and a4. So solutions, a1 is given to us. Now for a2, in this formula put n equals to 2. So we have left side is a2 equals to right hand side is 5 times a 2 minus 1 then minus 3. Here 5 times a 2 minus 1, that's the suffix 2 minus 1 minus 3. This equals to 5a1 minus 3 and put a1 equals to 2. So here 5 times 2 minus 3 equals to 7. So we found the second term is 7. Similarly, to find the third term, put n equals to 3 in this formula. So on left side, a3 equals to 5 times a 3 minus 1, then minus 3. 5a 3 minus 1, again 3 minus 1 is a suffix, minus 3. This equals to 5 a2 minus 3, then put a2 equals to 7, which you found in the earlier step. Then we will get a3 equals to 32. Similarly, a4 equals to 157. Hence, the first 4 terms of the sequence given by this formula is 2, 7, 32, 157. Great. I hope this makes sense to you all. Next, let's talk about explicit formula for the sequence. The idea: a sequence follows a pattern and first few terms suggest the pattern. So look for a pattern among terms and signs of the terms in the sequence. Example 3. Write an explicit formula for the nth term of the sequence given the first few terms are as follows. So here, first few terms of the sequence are 1, 1/3, 1/5, 1/7, dot dot dot. So here our denominators are odd numbers, increasing odd numbers. Here 1/1, next 1/3, next 1/5, next 1/7, dot dot dot. So let's find out that nth terms with this pattern. Just begin the solutions. So let's look for a pattern among the numerators and denominators separately. So here the first term is 1. We can write 1 equals to 1/1, and we keep the numerator 1 as it is. Keep the numerator 1 as it is, and for the denominator 1, rewrite 1 equals to 2 times 1 minus 1. So 2, then this purple one is for the suffix 1, and minus 1. So 2 times 1 minus 1 is 1, so it is there. Let's talk about the second term. Second term is 1/3. So then again, keep the numerator 1 as it is, and for the denominator 3, rewrite 3 equals to 2 times the suffix 2 minus 1. 2 times 3 is 4, 4 minus 1 is 3, which is here. Awesome. Next, the third term is 1/5. Third term is 1/5. So 1/5 equals to, keep the numerator as it is, and in the denominator, rewrite 5 equals to 2 times 3. 3 is the suffix for a here, and minus 1. So 2 times 3 is 6, minus 1 is 5, 5 here. Similarly, a4 is 1/2 times 4 minus 1, and now we have an idea. So the 10th term is a10 equals to 1/2 times 10 minus 1. So which suffix goes here? Same number goes inside the parenthesis here. Similarly, for the formula of the nth term, so an equals to, which is here, 1/2 times n minus 1. Hence, we found the formula for the nth term, an equals to 1/2n minus 1. I hope this idea makes sense to you all. Now, let's move on. Next, let's talk about factorials. Next definitions, factorials. Sometimes sequences are defined using a factorial, which is a product of consecutive natural numbers with all those that precede it. And factorial symbol is n, the exclamation sign, and read this one as n factorial. Example, n factorial equals to n times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1. So here we start from the n, and then we keep on decreasing the numbers by 1, and we multiply here all the way up to 1. In particular, 6 factorial equals to 6 times 6 minus 1, which is 5. So here 5. 5 times 5 minus 1, which is 4 here. 4 times 4 minus 1, which is 3 here. 3 times 2 times 1. This turns out to be 720. Note, 0 factorial is 1 and 1 factorial is always 1. Next example, write the fourth term of the sequence defined by this formula. an equals to n factorial over n plus 3 outside factorial. So solution, so for the fourth term, so let's put n equals to 4. So here a4 equals to 4 factorial over 4 plus 3, 7 factorial. Keep the numerator as it is in the next step, and the denominator, rewrite 7 factorial equals to 7 times 6 times 5 times 4 factorial. Because we do have 4 factorial in the numerator, so we stop here at 4 factorial. Now we can cancel the 4 factorial in numerator and denominator. Then this equals to 1/7 times 6 times 5, which turns out to be 1/210. Awesome. Quick remark. A sequence follows a pattern, and first few terms suggest that pattern. There are three types of sequence with a standard pattern: arithmetic sequence, geometric sequence, and harmonic sequence. Arithmetic sequence, we cover arithmetic sequence in next class in sections 10.2. Geometric sequence, after we cover arithmetic sequence, we cover geometric sequence in sections 10.3, again in another class. And harmonic sequence, which we do not cover in this class. So we study arithmetic and geometric sequences in coming classes. Next, let's talk about series and its notations. First, definitions. A series is the sum of all terms in the sequence. So if an is an infinite sequence, then the sum of the terms of the sequence, such as a1 plus a2 plus a3 plus ... is called an infinite series and is denoted by summations an, where this index n runs from 1 to infinite, or simply the summation an. The symbol, this, which is a Greek letter sigma, is called the summations or sigma notations. The integer n, this index n, is called the index of the sum. It tells you where to start the sum and where to end the sum. So for example, here, a1 plus a2 plus a3 plus ... plus ak. Then we can write this in short form as summations an, where n runs from 1 to k. Similarly, summations n equals to 1 to 50, means find the sum of an from n equals to 1 to 50. Similarly, summations n runs from 1 to infinite, means find the sum of an from n equals to 1 to infinite. So this sum is a finite sum, this sum is an infinite sum. Note, the lower limit of the summations can start with any numbers, not always with 1. So this sometimes can start from 0, sometimes can starts 1, sometimes can is 50, and so on. So this lower limit, so this starting point may not always be the 1. Next, let's do example 5. Compute each sum. In part A, summation n equals to 1 to 10. So on this summation, start at n equals to 1 and then stop at n equals to 10 and add all the terms of that series here. So n equals to 1 is 1, n equals to 2, n equals to 3, n equals to 4, ... n equals to 10. Add all those terms, which turns out to be the sum is 55. Similarly, in part B, summations 1 over 2 to the power n, and n runs from 1 to 5. So start from n equals to 1 and then stop at n equals to 5 and add all those terms, and in simplified form it turns out that the summation equals to 31 over 32. Great. I hope this summation makes sense to you all. Now, quick alert. A sequence is an ordered list of numbers and the series is the sum of a list of numbers. So sequence and series are different. Next, let's talk about partial sums. The nth partial sum of a series, the series is given by summations an and runs from 1 to infinite, is defined as capital N equals to summations ak. These ak's are the terms of this series, and summation starts from k equals to 1 and ends at capital N, which is same as Sn here. So this equals to a1 plus a2 plus ... a capital N. So S1 equals to a1, S2 equals to sum of the first two terms, a1 plus a2, S3 equals to sum of first three terms, a1 plus a2 plus a3, and so on. By the way, these partial sums means S1, S2, S3, ... forms a sequence called the sequence of partial sums. Next, let's do example 6. Find the fourth partial sum, that is S4, of the series. Given series is summations 1 over 2 to the power n equals to 1 to 7. So this equals to, this given series equals to, in expanded form, put n equals to 1, put n equals to 2, n equals to 3, dot dot dot, put n equals to 7. This turns out to be this sum on my right hand side here. So S4 equals to sum of the first 4 terms. So by formula, a1 plus a2 plus a3 plus a4, this equals to 1/2 plus 1/4 plus 1/8 plus 1/16. Let's add these fractions, make the same LCD. So here it's multiply by 8 over 8 to the first term. To the second term, multiply by 4 in numerator and denominator. To the third term, multiply by 2 on top and bottom. And then LCD is 16. Then add 8 plus 4 plus 2 plus 1. Simplifying, it gives us fourth partial sum S4 equals to 15 over 16. Awesome. Now let's move on. Next, let's talk about properties of summations. Given any real number k and natural number little n, the following are true. First, if we add n many constant, here's k is constant and the summations from 1 to n, then this equals to n times the constant. 2. Summations k runs from 1 to n equals to k equals to 1, k equals 2, k equals 3, dot dot dot, k equals to n. If we add 1 to n, then this turns out to be this fraction, n times n plus 1 over 2. Third, summations, the constant times the ai. We can pull the constant outside, so constant times the series ai. Third, we can distribute these summations over the sum as well as over the subtractions. 5, we can add the two series here. So for m between 1 and little n, summations ai runs from 1 to m plus summations ai runs from m plus 1 to n, then this turns out to be the single sum summations ai runs from 1 to n. I hope this makes sense to you all. So now let's do example 7. Compute the sum summations of 1 over 2 to the n plus n, and here the summation starts from n equals to 1 and ends at n equals to 5. Solutions. So by the property number 4, we can distribute this sum over this addition. So that means this equals to summations 1 over 2 to the n runs from 1 to 5 plus summation n runs from 1 to 5. Then this first series we already computed here in example 5. Example 5, this in part B, summation 1 over 2 to the n equals to 1 to 5 gives us 31 over 32. So let me copy that answer and put it here. So then this first sum equals to 31 over 32. In the second sum, summations n runs from 1 to 5 of n. So that means n equals to 1 plus n equals to 2 plus n equals to 3 plus n equals to 4 plus n equals to 5. So 1 plus 2 plus 3 plus 4 plus 5, this turns out to be 15. Now finally, let's add these two numbers here. So multiply 15 and divide 15 by 32. So LCD is 32. Then 31 plus 15 times 32. Then in the last step, the numerator turns out to be 511 and denominator is 32. Hence, this sum given in example 7 turns out to be 511 over 32. Great. I hope this makes sense to you all. We finished this sections 10.1 sequence and series, and in next class we will talk about arithmetic sequence in sections 10.2. 2. Thank you.